Hello, dear students. We are studying our mathematics paper 1, linear algebra, and we have already started unit number 3, vector space section 2nd. In previous video, we have seen dimension of a vector space, part 1. In that video, we have seen definition of dimension of a vector space and two most important result based on dimension of a vector space. First one was if dimension of a vector space is n, then any set containing more than n vector is linearly dependent. And second theorem, any two bases of a finite dimensional vector space has same number of elements. In this video, we are going to see another important theorem based on dimension of a vector space, and we'll see examples based on that result. So let us see theorem. Let Phi be n-dimensional vector space, then any set with n linearly independent vectors in vector space V is a basis for V. And second thing is that any set with n vectors which spans V is basis for V. In the definition of basis, we have seen that a set will be a basis if it is linearly independent as well as it spans V. But in this theorem, we are going to show that if n is n-dimensional vector space, then a set containing exactly n vectors will be a basis if it is either linearly independent or it spans V. First we prove this. Let n be V be n-dimensional vector space. Dimension of V is n. And first we have to show that any set with n linearly independent vector is a basis. So for that, we will consider a set B containing vectors V1, V2, etc. Pn be a set of n linearly independent vectors, means V1, V2, etc. Pn are linearly independent. We show that B is a basis. So our assumption is that B is linearly independent, and we have to show that B is a basis. So it remains to show that B spans V. B spans V means we have to show that any vector in V is a linear combination of vectors in V. So for that, choose an arbitrary vector V from vector space V, and we show that V is a linear combination of vectors in V. So let us consider a set B dash which is obtained from B joining a vector V to vectors in V. So B dash is V1, V2, etc. Vn and V. Since V is n-dimensional vector space, every vector in V containing more than n vector is linearly dependent. We have proved this result in previous video. So now this B dash has how many vectors? Total n plus 1 vectors. So this B dash has vectors greater than the dimension of vector, and therefore B dash is linearly dependent. And therefore there exist scalars k1, k2, etc. kn and k not all 0, such that the linear combination k1 v1 plus k2 v2 plus etc. kn vn plus kv equal to 0. Now let's see what happens if k equal to 0. So if k equal to 0, so from this equation we can have k1 v1 plus k2 v2 plus etc. kn vn equal to 0. Now but v1, v2, etc. vn are linearly independent, and in this step we have got a linear combination equal to 0, means each scalar is 0, that is k1 0, k2 0, etc. kn 0. So in this equation we have all scalars are 0, means the vectors phi1, phi2, phi and phi are linearly independent, but this is contradiction that b dash is linearly dependent, and therefore our assumption is wrong, means k never be 0. So we must have k is not equal to 0. So k is not equal to 0. So from this equation, you can shift the remaining vectors to RHS. So you will get k phi is minus of k1 p1 plus minus of k2 v2 plus etc. minus of kn vn. And since k is not equal to 0, you can divide throughout by k. So you will get phi equal to minus of k1 upon k times v1 plus minus of k2 upon k times v2 plus etc. minus of kn times k upon vn. If you want, you can rename this scalar as alpha 1, this is alpha 2, etc. This is alpha n. So you will get phi is alpha 1 v1 plus alpha 2 v2 plus etc. alpha n vn. And from this, we can say that phi, this vector phi is linear combination of p1, p2, etc. vn, as phi is arbitrary vector in V and is linear combination of vectors in B. We say that every vector in V is linear combination of vectors in B, and therefore you can say that B spans V. Thus we have B is linearly independent and B spans V, and therefore by definition of basis of a vector space, B is a basis for V. So in this case, we assume that B is linearly independent, and we prove that B is a spanning set for V, and therefore B is a basis for vector space V. Secondly, we show that any set with n vectors under the condition that this vector spans V is a basis for V. So for that, suppose that B containing n vectors p1, p2, etc. pn, and assume that B spans V. B spans V means every vector in V is linear combination of vectors in B. We have to show that this B is a basis, and our assumption is that B spans V. So it remains to show that B is linearly independent. Let us prove this result by contradiction. So if possible, let us see what happens if B is linearly dependent. So if possible, suppose that B is linearly dependent. So by the definition of, by the linear dependence, we say that if a set is linearly dependent, at least one vector in that set can be expressed as linear combination of rest of the vectors in the same set. This result we have proved in the video which is made under the title linear dependence and independence. So here B is linearly dependent, so at least one vector, we can say that Vi is linear combination of rest of the vectors in B. So we must have Vi is k1 p1 plus k2 v2 plus etc. ki minus 1 Vi minus 1 plus ki plus 1 Vi plus 1 plus etc. kn pn. Now consider the set B dash, which containing the vectors in B except for Vi. So B dash is p1, p2, etc. Vi minus 1, Vi plus 1, Pn. So how many vectors are there? Total n minus 1 vectors. And here we have showed that Vi is linear combination of n minus 1 vectors. So as B spans V, every vector in V is also a linear combination of vectors in B dash, because this B dash is contained in V, and therefore B dash spans V and B dash contains n minus 1 vectors. So which is not possible because dimension of V is n, means exactly n number of vectors spans B. So here we have proved that B dash spans V and B dash containing n minus 1 vectors. So which is not possible since dimension of V is n, and therefore our assumption is wrong, means B must be linearly independent. Thus B spans V and B is linearly independent, hence B is a basis for vector space V. So in the second case, we assume that B spans V and we prove that B is linearly independent, and hence we conclude that B is a basis for vector space V. So this is very important result in the linear algebra. So we conclude this remark from above theorem. We say that if dimension of V is n, then this is important, then any set with n vector is a basis for V if it is either linearly independent or it spans V. So if you have given a set and you ask to verify whether given set is a basis for given vector space, then identify the dimension of given vector space, count the total number of vectors in the given set, and if these two are same, then you should check whether given set is linearly independent or given set spans V. If either one of these two conditions hold, then you conclude that given set is a basis for vector space V. Let us see such type of examples. So determine whether the set of vectors are from R3, 1, 2, minus 3, then 1, minus 3, 2, and then 2, minus 1, 5. Determine whether this set is a basis for R3. Now here, what is the dimension of R3? So dimension of R3 is 3. What are the number of elements in the given set? This is 1, this is 2, and this is 3. So given set contains exactly 3 vectors. So this set will be basis for R3 if it is either linearly independent or it spans V. But to show that given set spans a given vector space, so it is quite difficult. So it is easy to check whether given set is linearly independent or not. So you can rename these vectors as V1 is order triplet 1, 2, minus 3, V2 is 1, minus 3, 2, V3 is 2, minus 1, 5. Now since dimension of R3, here I have forgot to give the dimension. So if dimension of R3 is 3 and given set B contains exactly 3 vectors, so it is sufficient to check whether B is linearly independent or not. So if B is linearly independent, directly you conclude that B is a basis. If B is not linearly independent, you conclude that given set is not a basis. Now to check linear dependence, we consider the linear combination of given vectors k1 v1 plus k2 v2 plus k3 v3 equal to 0. So put vector v1 here. So k1 times 1, 2, minus 3 plus k2 times v2 vector is 1, minus 3, 2 plus k3 v3 vector is 2, minus 1, 5. Simplify this LHS. So you will get first component is k1 plus k2 plus 2k3. Second component 2k1 minus 3k2 plus minus k3, and third component minus 3k1 plus 2k2 plus 5k3 equal to 0. 0 is this 0, 0, 0 is additive identity in R3. So equating component, we will get k1 plus k2 plus 2k3 is 0, 2k1 minus 3k2 minus k3 equal to 0, minus 3k1 plus 2k2 plus 5k3 equal to 0. Now we are looking for the values of K1, K2, K3. So now this is homogeneous system of how many equations? 3 equations in how many unknowns? 3 unknowns. So homogeneous equation of 3 equations in 3 unknowns. So to determine K1, K2, K3, you can apply Gauss elimination method or Gauss-Jordan method. These methods we have seen in unit number 1. So you must try these methods and find the values of K1, K2, K3. Alternatively, we can apply the determinant criteria. So what is that determinant criteria? So let us see. If AX is a homogeneous system of n equations and n unknowns, that is important. Determinant criteria is applicable for the homogeneous system having same number of equations equal to the number of unknowns. Then system has only a trivial. Trivial means zero solution if determinant A is not equal to 0. And if determinant A equal to 0, then system has non-trivial means non-zero solution, means infinitely many solutions. So remember this. What is this A? A is the coefficient matrix. So if determinant of coefficient matrix is not equal to 0, then system has zero solution. And if determinant of coefficient matrix is equal to 0, system has non-zero solution. Now in this case, we have coefficient matrix having first row 1, 1, 2, 2 minus 3 minus 1, second row, and third row is minus 3, 2, 5. So this is 3 by 3 matrix. So compute this determinant and it is minus 3, and obviously it is not equal to 0. So determinant of coefficient matrix is not equal to 0. So what is the conclusion? System has only a zero solution, means K1 equal to 0, K2 equal to 0, K3 equal to 0. Thus, we have linear combination K1V1 plus K2V2 plus K3V3 equal to 0 implies each scalar equal to 0. So, what is the conclusion? Conclusion is that given vectors V1, V2 and V3 are linearly independent, and thus B is linearly independent, and hence B is a basis for vector space R3. So it is quite easy to check whether given set is a basis for given vector space or not. Let us see another example. Show that the set of vectors, these are the matrices. So first matrix 1 0 minus 1 2, second matrix 0 minus 1 minus 1 0, third matrix 0 minus 8 minus 12 minus 4, fourth matrix 3 6 3 minus 6, and we have to show that this is a basis for the vector space into R. What is this? This is the set of all 2 by 2 matrices with a real entrance. So again, what is the dimension of this vector space M to R? So M by N R dimension is M into N. Here M 2 by 2. So dimension is 2 into 2, that is 4. So dimension of vector space is 4. How many vectors are given in the set? So total 4 vectors. So it is sufficient to check whether given set is linearly independent or not. You can rename these matrices are A1, A2, A3 and A4. Since dimension of M2 is 4 and given set contains exactly 4 vectors, so it is sufficient to check whether B is linearly independent or not. So for that we have to consider a linear combination K1A1 plus K2A2 plus K3A3 plus K4A4 equal to 0. So what is this RHS 0? 0 of vector space M2 R, and that is 0 matrix of order 2. Now simplify LHS, and 2 matrices are equal if components are equal. So A11 equal to A11, etc. So equating, we will get K1 plus 3, K4 equal to 0, minus K2 minus 8, K3 plus 6, K4 equal to 0, minus K1 minus K2 minus 12, K3 plus 3, K4 equal to 0. 2k1 minus 4k3 minus 6k4 equal to 0. Again we got homogeneous system of 4 equations in 4 unknowns. So this is the homogeneous system of 4 equations in 4 unknowns. So again, number of equation is equal to number of unknowns. So we can apply determinant criteria. So coefficient matrix, write down the coefficient matrix and find out its determinant. So here determinant of coefficient matrix, this is coefficient matrix, this is matrix of order 4. So you can compute its determinant like this: 1, and then respective row, column and row will be deleted. Then determinant of square submatrix of order 3. So 1 times this, then minus 3. These middle 2 are 0. So directly minus 3 times. Delete this row and this column. So determinant of square submatrix of order 3. So simplify this, and this is minus 96, obviously not equal to 0. So determinant not equal to 0. What is the conclusion? System has which type of solution? Only a trivial solution, means all scalars k1, k2, k3 are 0. So thus we have linear combination k1a1 plus k2a2 plus k3a3 plus k4a4 equal to 0, implies k1, k2, k3, k4 all are 0. So what is the conclusion? Conclusion is that these vectors a1, a2, a3 are linearly independent, and hence the set is a basis for M to R. Next example, for the vector space P2X. So what is this vector space P2? P2 is vector space of all polynomials of degree less than or equal to 2. So we have given set of vectors P1, P2, P3 here. P1 is 1 minus x plus x square. P2 is given 1 plus x, and P3 is given 2 minus x minus x square. So we have to determine again whether this is a basis for vector space P2 or not. So what is the dimension of P2x? Pnx is n plus 1. So what is n here? N is 2. So dimension of P2x is 3. Now given vectors are 3. So it is sufficient to check whether given vectors are linearly independent or not. So consider the linear combination k1p1 plus k2p2 plus k3p3 equal to 0. This 0 will be the 0 polynomial in P2. So put P1, P2 and P3 here. So simplify this. Now equating coefficients of x raised to 0, x raised to 1 and x square on both sides. So you will get k1 plus k2 plus k3 equal to 0, minus 2k1 minus 2k2 minus 2k3 equal to 0, k1 plus 0k2 plus k3 equal to 0. Again, this is a homogeneous system. So we can apply determinant criteria. So write down the coefficient matrix. Coefficient matrix is this one, and determinant is 0. See here we got determinant of coefficient matrix is 0. Then what is the conclusion? Determinant is 0. System has non-zero or non-trivial solution. Non-trivial means infinitely many. That is, there exist scalars k1, k2, k3, not all 0, such that the linear combination k1p1 plus k2p2 plus k3p3 equal to 0. And therefore, these vectors are linearly dependent. And since the given set is linearly dependent, it is not a basis for given vector space. So these examples, you can go through all these examples, and I have given some exercises, and you can solve these examples at your phones. And for first example, this set will be a basis, and for second example, this set will not be the basis. Answer is given since maybe given set is linearly dependent. So we can verify these sets are basis for given vector space or not. So we'll stop here. In the next lecture, we are going to see again more important results based on dimension of a vector space. Let us stop here.